So let me begin by giving some general introduction. Okay. So as you know, black holes in two derivative theory in asymptotically flat d-dimensional space-time can carry typically a set of U1 charges, angular momentum. Okay, that in higher dimension there will be more than one angular momentum in the Cartan subalgebra, and mass. And the Bekenstein-Hawking entropy is given by area over 4 times the Newton's constant, and that's expressed as a function of the charge, mass, and the angular momentum. Okay. And even though I'm denoting the charge and angular momentum by single variables, these you should really think of as vectors. So these can have multiple components. So one can derive a scaling property of the entropy by noting that if you have a two derivative action, then this scales as lambda to the d minus 2 if you scale the metric, the two-form field, and the gauge fields in this way. And from this, it follows that the entropy has a similar scaling property because the entropy scales as the action. And that scaling property takes the form that if you scale q by lambda to the d minus 3, m by lambda to the d minus 3, and j by lambda to the d minus 2, the entropy scales by lambda to the d minus 2. So in 4 dimension, this corresponds to scaling q and m by lambda and the angular momentum by lambda square. Yes. Yeah, space-time dimension. Yeah.
And you can get this q scaling by doing the Gaussian integral?
Yeah, you can get it by Gaussian integral. Yeah. Q and m scaling you can both get by Gaussian integral. Okay. Or you just use the fact that the field strength falls off as 1 over r to the d minus 2. Yeah.
And in the same way, the metric falls, the short chain metric falls, like 1 over r d minus 3.
Exactly. Yeah.
Okay, and the j is that with an extra factor of?
Yeah, j t phi. You look at the j t phi and how it falls off, and from that you can figure out how j scales. Yes. Higher charges because you are considering a black hole, right? Not a black brane or something. So if I have a black brane, then that carries higher form charges, right? We are just considering a point-like object in this case. Because entropy really makes sense only for point-like objects. Otherwise, I'll talk about entropy density. Okay, so this also suggests that there is a way to take the macroscopic limit, that we simply use these scalings. Okay. So we scale the mass, charge, and angular momentum in this way, and just take lambda to be large. Okay. And in this limit, the black hole entropy scales as lambda to the d minus 2. And in this limit, it's also clear that all the higher derivative corrections will go to 0. They'll be scaling at lower powers of lambda.
So this B mu, A mu, these are gauge fields.
Yeah, this is a two-form field. B mu is the two-form field that comes from the Skull-Bromont field, right? The string theory has a B mu, right? If the black hole is not rotating, typically B mu is not excited, so B mu is just set to 0. For a rotating black hole, you can get non-zero B mu.
These correction calculations that we do, these are string theory calculations or field theory calculations?
We'll be focusing mostly on the field theory calculations. I'll discuss the various corrections that can appear, right? But our focus will be mainly on something that comes from just field theory, massless fields. Exactly. Yeah.
And Ashok, just for context, suppose I was considering one conformal field theory in capital K dimension.
Yes.
Then the scalings would be completely right there.
Yeah.
Mass would scale like d lambda to the power d, charge like lambda to the power d minus 1, and entropy also like lambda to the power d minus 1. Right? Because there's like temperature to 1.
Probably, yeah, maybe because those are that will be like a boundary.
I was thinking just dimension.
Okay.
So temperature to the power d with the volume factor, and then temperature to the power d will give you mass.
Okay, I think the point is, yeah, you are thinking in terms of whether you have said h bar equal to 1 and g equal to 1. Here there is no h bar. This is classical, right? I think in the conformal field theory there is no g. So they are the Newton's constant.
Yeah.
So they are the scalings are all done by h bar, right? You are setting h bar equal to 0 and then just counting dimensions. Here it's more like you are setting g equal to 1, right? And counting dimensions.
That's another way of finding it.
Yeah. Exactly. Because there's no H bar here anywhere, right?
Right. So, but again, the final result would be very different. Though in
Yeah.
ATS, it would become the scaling factor.
Yeah, exactly.
This F function is the entropy.
Yeah, F function is the entropy. Same. Yeah, this function over here. Yeah. That is some function of the charges and the masses and the angular momentum.
And of course, one striking thing here is that the entropy scales faster than mass.
Yeah, entropy has because like entropy grows as m square, right? In 4 dimension also, you know that entropy goes as m square.
Whereas in a conforming field theory, it goes lower.
Yeah, that is true.
Right, because sub.
Yeah. Okay. So we'll also need to deal with these chemical potentials. Okay, so this is like the inverse temperature. This is the chemical potential dual to charge, and this is the chemical potential dual to angular momentum, okay, which are defined this way. And just by the scaling of the entropy and the mass and the charge and the angular momentum, we can figure out how these things should scale. Right? So, for example, the entropy scales as lambda to the d minus 2, m scales as lambda to the d minus 3, and from that it follows that beta will scale as lambda. Okay. Similarly, here this goes as lambda to the d minus 2, this goes as lambda to the d minus 3. So this partial derivative will scale as lambda, but then beta also scales as lambda. So mu will scale as 1, and omega will scale as lambda inverse, because J has 1 higher power of lambda. Okay. So this is all in theories where we have only 2 derivatives. These are going to get corrected at once you include hard derivative corrections and loop corrections.
Right. And beta goes like lambda, roughly in short chain geometry, that beta goes like 1 over RH.
Yeah, exactly.
And omega goes like 1 over lambda, because roughly that goes like RH. Is that right?
Omega, no, lambda, no,
Halfway
beta goes as RH. Beta is the inverse temperature, right? Yeah, beta goes as RH, yeah.
Beta.
Yeah.
And omega was like 1 over RH.
Omega, I think, goes as 1 over RH, yeah.
Like, it's fast.
Yeah, because J has 1 extra power of lambda, right? So that makes it 1 over RH. Okay, so now we want to study corrections to this formula. Okay. So one set of corrections come from Wald's formula. Okay. So these Wald's formula is designed to give correction to the entropy formula under hard derivative corrections. Okay. So for example, if we have classical hard derivative terms in as it appears in string theory, okay, they can be dealt with by using Wald's formula. Or if you have loop corrected 1pi effective action, then the local part of the loop corrected 1pi effective action, which has a derivative expansion, that also can be dealt with Wald's formula. Yeah, exactly. So those certainly will not be dealt by the Wald's formula, right? So I'll discuss here how the log terms come. So anything that you can calculate using Wald's formula will basically have a power series expansion in 1 over lambda, right? This will be suppressed by inverse powers of lambda, because the more derivatives you have in the action, there will be more powers of lambda in the denominator, because you have to contract those derivatives with inverse power of metric, right? And the metric carries a lambda square. But due to presence of massless states in the massless states, the loop corrected 1pi effective action will also contain non-local terms. And the contribution from these non-local terms to the entropy cannot be computed using Wald's formula. Instead, we need to directly evaluate the path integral over the massless fields in the black hole background. And the idea is that the reason that this that you cannot first calculate an effective action and then evaluate it is that the infrared cutoff is provided by the black hole size itself, right? So if you try to remove the black hole size, then the infrared cutoff disappears and you cannot evaluate the 1pi effective action. So because of this, we have to deal with this directly, okay? Namely that you have to directly evaluate the path integral in the black hole background, and that's where these logarithmic term corrections come from. Okay? That's the origin of the log lambda terms in the entropy, and these is what we'll focus on.
The non-log lambda terms would be order 1 and then 1 over lambda squared.
Exactly.
It's a power series.
Yeah, there will be a power series expansion in 1 over lambda squared. Right? Because every time you add two derivatives, and that you need that contracting those two derivatives will require an inverse part of the metric, which will produce 1 over lambda squared.
That's the part.
Yes,
Part of the part.
I would think so. Yeah, if you are trying to do the entanglement entropy calculation in the bulk, I think the logarithmic corrections will come in the bulk entropy formula. Yeah.
Sorry, the classical part was lambda to some what, d minus 2.
D minus 2.
First, non-logarithmic correction, would that be order 1?
Depends on the D, right? In 5 dimension, it will start at lambda cube and then the order lambda term.
So just classical and then
Exactly. Yeah. So in 4 dimension, the logarithmic terms are the dominant corrections, right? Because you start with lambda square, right? Then there is log lambda and then the order 1 correction, right? So in 4 dimension, log corrections are dominant. In 5 dimension, you start with lambda cube, then the order lambda correction, then there is logarithmic correction. Okay. So we will not discuss some aspects of the path integral in the presence of gravity, because this is what we need to compute these log corrections. Okay. So here there are two sides of the story. The gravitational side will be to perform a path integral over all fields, weighted as usual by exponential minus action times some functional of fields.
So sorry.
Yeah.
But if I was doing G Newton counting,
Hmm.
then the classical term is 1 over G Newton.
Yes.
The first logarithm, for ignoring logs, the first one loop would be order 1. Is that right?
Classical, no, G Newton has different dimensions in different different space-time dimensions, right? So first one will not be of order 1.
Will not be order. I was thinking that just if we do this, I think of 1 over G Newton as a coupling constant. Classical term is 1 over coupling constant, and then the first quantum correction is usually order 1.
But there are stringy corrections, right?
Okay.
Which will be alpha prime.
Which will be alpha.
Right?
5 dimensional.
Yeah.
But in counting in G string, it would be order 1 in G string.
No, order 1 over G square in G string. The classical higher derivative terms. Yeah.
And then the first correction would be order 1 in G string.
When you do G string expansion.
Yes.
I think when you do G string expansion, even then I'm not sure that first correction will be of order 1, because in 10 dimension, for example, right? When you do the G string expansion, that order G string square, there can be Riemann square correction. I don't think because in the loops, right, all the higher massive states are propagating, right? So the expansion there is not in G Newton, it is in G string, right, which is a dimensionless quantity.
Yes.
Right? And then the dimensions are fixed by the dimension of the operators.
But,
Right.
so the G string counting isn't the classical term 1 over G squared, and then the first loop correction 1.
Yes. Yeah. In G string it's 1.
It's G
Right.
string. Fine.
Yeah. But the dimension,
Yeah.
Right.
The dimension could be low.
yeah,
Right. So this lambda, right? Because of this one, the lambda and G string expansion are completely different.
yeah, not completely different, but different.
Different.
Right.
Had it been only gravity, no higher scope states, just G Newton, then you could relate that.
Yeah, the point is okay. Even if had it been just gravity and if the UV cutoff had been the Planck scale, then I think what you are saying is true. Yeah,
Had it been the only length.
Yeah. Had it been the only length scale, yeah,
Then you could.
then maybe yeah. But in string theory, certainly that is not the case, right? Because you will have order lambda corrections.
In this case, it's string theory, G of order 1.
No, even if G is of order 1, right, the low energy effective action correction in string theory will start with the leading term is root GR, right? Then the Riemann square correction, right? That will be there even in 10 dimensions in string theory.
But alpha prime and G of order 1, alpha prime and the Planck scale are the same.
But alpha, the expansion is in parts of alpha prime, right? which is a fraction of G Newton.
But it's order one fraction, if G is order. G is string coupled.
Yeah, but G Newton is a dimension full quantity, right?
Yes. Oh, I see. You're saying that it's, but you can get fractional power.
Fractional power, yeah,
Okay,
exactly. So in G Newton, you can get fractional power. Yeah. Okay. So the gravitational side of the calculation that we'll be doing is to do a path integral weighted by exponential minus action times f, where f is a suitable functional of the fields. Okay, mostly f will be 1, but we'll see that in some cases we'll choose different f. And you have to put appropriate boundary conditions in the Euclidean theory. So this path integral, of course, is done in the Euclidean theory. And what it computes, and this is a statistical interpretation, is a partition function of this kind, okay, which is trace of e to the minus beta h minus beta mu dot q minus beta omega dot j times the same functional f that you have here. And the important point here is that which is the ensemble in which you carry out the trace. And as we will see, the ensemble that we use to evaluate the trace is correlated with what boundary condition you put on the fields in the path. And these boundary conditions in turn are dictated by setting the dominant modes of the fields to 0. Right? You have to keep the dominant modes fixed or 0 or some constant. Okay, the dominant modes of the fields you have to set to some constant, and then the subdominant modes fluctuate. That's the natural boundary condition. Okay? And that in turn will determine what ensemble we compute the trace here. Okay? And that is the equality. That this path integral will basically compute this trace in that ensemble. Yes.
Right.
Yes.
Trace interpretation. Right.
Yeah. So you are thinking of this trace as viewed from an asymptotic observer's viewpoint, right? Exactly. Right. I mean, I'm not thinking of this as an ADS, right? But imagine there is an asymptotic observer who is trying to calculate the trace over all the states, right? And that trace is related to this gravitational path integral which is given here.
And relatively, we see it as a trace only if you added classical plus one loop. One
Yeah.
loop itself will not have the property.
Yeah, exactly. Yeah. Yeah. The total partition function will have the property of a trace. Yeah. Okay. So I'll be discussing 3 examples, right, which uses different kind of gravitational path integral, and correspondingly it will have different kinds of trace. So the first example is in fact the standard Gibbon-Sucking example. So you can carry out a path integral in asymptotically flat space-time. So in asymptotically flat space-time, if you look at the tau component of the metric at infinity, then in the classical solution, this tau component of the metric will have a constant piece, and then there will be a piece which is proportional to r to the minus d plus 3. So in 4 dimensions, you are familiar with this. It's the metric at infinity goes as 1 minus 2gm over r, 2gm over r, right? Those are these 2 constants over here. So tau is the Euclidean time. We fix the period of the Euclidean time, say, to be 2 pi. That's just normalizing tau. Now, if we just examine this, and we will be working always in dimensions larger than 3, right? Just to avoid confusion with this various problems with conical defects and so on. So for dimension larger than 3, here we can see that the mode A is dominant because this falls off faster as at large r. And so then the rules for carrying out the path integral on the gravity side will be to fix A to some constant and then let B fluctuate. And B in this case is essentially encoding the energy or the mass of the solution. So we fix the period, okay, g tau, and we let the mass fluctuate.
And this is, of course, a natural thing to do. But can you modify the path integral by adding some boundary term or something like that?
Well, you can add boundary term. That is not the problem, right? That tells you what to do with the classical saddle point. But after that, what mode you should keep and what mode you should not keep, okay? That becomes a headache. At least we have not figured out a systematic way to carry out this path integral at fixed mass.
But I would have thought effectively doing the Legendre transform as part of the path integral would do that.
Yeah, but how do, I mean, systematically make the Legendre transform into part of the path integral, right?
How about putting a mode at infinity that couples to the mass?
Putting, yeah, the point is that, I mean, you can change one, you know that you have to do Legendre transform. So you can say, okay, that mode you will include. But then what is the rule? What about other fields, right? What boundary conditions? I mean, you have to put a uniform rule for putting boundary conditions of various fields, right? So knowing the answer, you can always devise a rule, right?
Yeah.
Which is like as you said, like effectively doing Legendre transform,
yeah.
Right? But we have to have a priori prescription of what are the modes you should integrate over, right? And that becomes a very hard thing to decide in this case.
In ADS, sometimes this is possible.
In some window it is possible. Yeah. But only in a window, right? Yeah. Yeah.
Okay.
And that also only for the scalars, right? For hard fields, I don't know how to change the boundary condition. Yeah, of course. Once you can do this, you can do the Legendre transform. That's a confusion. Yeah. And the path integral, can you set up a systematic procedure to change the ensemble, right? Exactly.
But if these charge fields can't be moved in other way instead of.
No, you can change boundary term, right? Boundary term. But then what will be your rules for which modes to integrate over? At least we have not been able to. For example, we tried very hard to see if we can get the grand canonical ensemble in ADS2 times S2 or microcanonical in flat space time, and to find a fully systematic procedure seems to be very hard. At least we couldn't figure out a consistent set of rules that will allow us to do that.
Dirichlet versus Neumann choice there.
Yeah, but the point is the way you fix the boundary condition is that you demand square integrability, right? So once you give up square integrability of one of the modes, right, then how do you decide what condition you will put on the other modes?
We're just doing path integral over this thing.
No, over all the fields, right? So including G. That's okay. We'll just do a Euclidean rotation and do the integral. Yeah, the standard Euclidean rotation. So that doesn't seem to cause any confusion, right? Particularly because you are only looking at one loop determinant, right? You are not trying to get a non-perturbative result. Right? So the while mode integral, we can just do the weak rotation. Yeah. So the issue of boundary condition is that here it seems natural from here that A is a dominant mode, right? So we'll keep this fixed at infinity, right? So we'll demand that whatever field fluctuations we allow, right, we'll have to have same G tau tau at infinity, right? Which we fix. That will be some parameter. That will be in fact the inverse temperature, as we'll see. Right? And then we let all the other modes fluctuate, right? No non-observable modes fluctuate. So that's the natural boundary condition. That's what we'll use, right? I think the question was about whether you can use some unnatural boundary condition, right? Where you say let this mode fluctuate and keep B fixed, right? Exactly. Yeah. So this you can see here, right? So once you keep this fixed, right, then the period is just 2 pi times square root of G tau tau, right? So fixing A basically means you are fixing the temperature or the inverse temperature. Yeah, GRR and all can fluctuate.
Just to remember, I thought in ABS4 can you for a gauge field, then you can do both boundary.
Okay, ADS4 gauge field, I'm not completely sure. Maybe you can. Maybe you can do that. Yeah, it's possible. Maybe, yeah.
You can by adding about make what the mode was that was not normalizable, make it normalizable and add a Chern-Simons instead of coupling it. That basically gives you this mixture.
Yeah, for scalars, if I remember, both modes are normalizable to begin with, right? That's how you can switch.
With the right counter.
Yeah, with the right counter term, exactly.
both fall.
Both fall.
Both fall, and to make it square integrable, you need a couplet.
Yeah.
You need an appropriate couplet.
Yeah.
I mean, in areas it's easier because volume and area are the same.
Yeah, exactly.
So,
So with an area you can cancel the volume, right?
Yeah.
Yeah. Yes. Well, constant is also flat, right? You can make it 1, but I have just fixed the period of tau to be 2 pi. Right, so that's why the g tau I can I allow to fluctuate. Yeah, I allow to fix to some constant.
That put that 1 and then the period of tau.
Exactly. Yeah. Right. I just did it this way because then it has become clear that it's a fluctuation of the metric. Okay. So similarly, in the same setting, okay, at infinity, the tau component of the gauge field has this form. Right. This I beta mu. This is just I've just chosen this constant to be this one. Okay, just some constant plus q times r to the minus d plus 3. Again, a constant and 1 over r. Right. In d equal to 4, we are familiar with this fact that the gauge field has asymptotically can go to a constant and then there's a 1 over r piece. Right. And again, we see that this mode is dominant. Right, because this falls off. For d larger than 3, this falls off, this is dominant. Okay. And so the natural boundary condition will be to fix this. Beta we have already fixed, right? Beta was this period that we had here. So the natural boundary condition is that we fix mu and let this mode fluctuate, and this mode letting this fluctuate means that we let the charge fluctuate. Okay. So in the corresponding ensemble on the statistical side, we basically sum over all charges. And similarly, one can do an analysis of the g tau phi, right? Again, the dominant part of g tau phi has to be fixed. The subdominant part has to we have to let the subdominant part fluctuate, and that basically means that the angular momentum we have to allow to fluctuate, and we keep the omega fixed, right? The chemical potential. So the conclusion then is that in this case, in asymptotically flat d-dimensional spacetime, the gravitational path integral with boundary conditions on the metric and gauge fields are set by beta, mu, and omega. Okay. And what it computes is the partition function z in the grand canonical ensemble, right? Which is given here. You're always integrated than 3. Okay. So the grand canonical ensemble means basically you integrate or sum. Okay, I've replaced the sum by integral. Okay, at this level it doesn't matter. We integrate over all possible quantum numbers, okay, which includes the mass, the charge, the angular momentum, and also the momentum that the black hole carries. And so the weight, it's weighted by the degeneracy, okay, which is basically the exponents of the entropy. This is what we are trying to calculate, right? But gravitational path integral actually calculates this. Okay. So you have to invert this to actually calculate S in terms of Z. Okay, otherwise we have this formula, and here this you had an e to the minus beta I. I have just replaced E by m plus k square over 2m. You can include the higher powers of k, but it will not make a difference for what calculation will be doing, right? So I have just truncated the square root of k square plus m square to the quadratic order.
Sorry, I should probably very.
Yeah.
But when going from the sum to the integral in this mass,
yeah,
this mass is probably measured in classical, meaning mass of order 1 by g square is measured as 1 here.
Yeah, g square I'm not counting here. G I'm thinking of order 1, right? Maybe 1/10, whatever, right?
Yeah.
So I mean, I'm not distinguishing between the string scale and the Planck scale in this analysis.
Suppose I want to keep. Suppose I was just doing that, and I want to keep track of powers of g Newton.
Yes.
Now, if that SMQJ was a classical formula, then the sum and the integral would have an extra measure factor of G of Newton's constant to some power.
Okay.
Outside, and then you get extra factors of log Newton's constant from
okay.
that. But that's not, I know, of your interest, but that's correct. Right?
Yeah. Which probably one can fix just by dimensional analysis at the end.
Because it's a log there.
Oh, log.
Because it'll be log outside. It's just the fact that
In the entropy.
in the
Yeah, in the entropy. Yeah. Okay. But I'm saying before you calculate the entropy, right? Z is dimensionless, right? In Z, you can figure out probably what the power should be.
yeah.
Yeah. See, it's log of, even log, right? It's log of the mass and other things, right? So they have to be normalized by something, right? So that the G Newton basically will enter there.
My question was really motivated by ADS, where you could get a log n,
Yeah, true.
a factor of log n, which then was dimensionless.
Yeah.
And that would have to be kept track of.
I agree. Yeah. Because in ADS, what you have to do is that when you scale, right? This scaling is not true, not valid in ADS, right? So the scaling will be, if you want to apply this to in ADS, the lambda scaling will also apply on the cosmological constant, right? You have to scale the cosmological constant also appropriately.
But I was just asking, sorry, very irritating, but just about the simple kinematical fact about going from microcanonical to canonical.
Yeah.
Considering with the sum over all charges.
Yes.
There. But then if you wanted to convert that in an integral in terms of charges that are measured in units of n squared, you will get n squared to the power number of integrals you done.
I agree.
N
Yeah.
squared to the power.
Yeah. Yeah. I
And
agree.
you get log of n squared.
Yeah. I agree. Yeah. One way to avoid this is to think of this charge as being quantized in integer units. This is integer quantized charge. Then sum over q is the same as integral over q.
Exactly. But that's not the way we write the classical form.
I agree. Yeah. But if you think in as a charge as being quantized charge, right? Because I'm always thinking of the charge as being quantized in integer units.
Perfect.
Right?
Perfect.
Then there is no confusion between integral and sum.
So that's exactly the logic that gives you the n squared power.
Exactly. Yeah. Okay. And here just I wanted to say these integrals are multi-dimensional integrals. This momentum, so when you do the momentum integral, this includes only momenta along directions that are invariant under beta omega dot j. Because of course you cannot, if the part of the momentum that doesn't commute with this, that doesn't appear in that trace, right? If there is a state that carries that momentum, then this will rotate that momentum, right? So it will just not contribute to the trace. So those components you have to set equal to 0. You only integrate over those momenta that are invariant under beta omega dot j. Okay. So the point is that, so this side you know, right? Left hand side. The right hand side one doesn't know. Right hand side, what one can do is to evaluate using a saddle point method, because our ultimate goal is to relate S to log of Z. So you evaluate the right hand side using a saddle point method, and the saddle point, of course, is located at the wherever this is extremized, so which corresponds to k equal to 0, and then you have to use this del S del M equal to beta, del S del Q equal to beta mu, and del S del J equal to beta omega, okay, by extremizing the exponent. Okay. And these are exactly the way we define the beta mu and omega earlier, right, in the for the black hole. But the important point is that there will be fluctuation determinant around the saddle point. That when you do these integrals, there will be fluctuation determinant around the saddle point, and those can produce additional log lambda terms. And here is just an example. Okay, that suppose you look at the M integral. M integral will produce a factor of the second derivative of S with respect to M squared to the minus half. The second derivative of the exponent, this part actually doesn't do very much. The second derivative of the exponent is basically coming from this derivative, and that produces a factor like this, right? Because S goes as lambda to the d minus 2, M goes as lambda to the d minus 3. Okay? So that's altogether lambda to the d minus 4 by 2. Okay? So when you do this integral on the right hand side, you will get a factor of lambda to the d minus 4 by 2. So when you bring it to the left hand side, because you are trying to express S in terms of log Z, we see that you will get an extra contribution of minus d minus 4 by 2 log lambda in the entropy, okay, from these integrals. And the similar factors will come from the k integral, the q integral, and the j integral. Okay, all of these will give additional powers of log lambda that you have to keep track of. So this is besides what you will get in Z. So later on I'll describe how to calculate the log lambda terms in Z. Okay, but just from the change in ensemble you'll get some log lambda terms. In 4D, yeah, this one doesn't contribute, but there are other things which can contribute. Right? For example, the del 2 from name integral, yes. In general, will contribute, yeah. In fact, from the Q also, I think there is a contribution because Q and M scale in the same way. But from the J, there will be some contribution. In 4, I think 4 dimension is spatial somehow. Yeah. Because A goes as M square, right? So the second derivative somehow doesn't scale.
Physically, it's a measure of the range of M's that are contributing to this.
That's right, yeah. How thick the M interval is, exactly.
And
yeah.
So in 4 dimensions, that large, a very large lambda, that thickness stays one.
Exactly, yeah. Okay. So now I'll discuss second example. Here we work in the near horizon geometry. This is for the extremal ones. So you work in the near horizon, ADS 2 times K, okay, where K is some compact space. So K typically, if you are a 4-dimensional black hole, then K is typically a sphere, okay, or if it's a rotating black hole, K is a deformed sphere. In higher dimension, K is some version of sphere or deformed sphere. So the ADS part has this structure, okay, where with some constant A, which is the ADS size, and R and tau are the coordinates. Tau has period 2 pi, right? That's when this conical singularity goes away. Now, in this case, if you look at large R, right, and look for the solution to the Maxwell's equation, one finds that the gauge field has the 2 independent solutions for the, say, A tau, have this structure. There is a constant part which is always there because a constant A tau, of course, always solves the equation of motion, right? Because F is 0 for constant A tau. But the R dependent part now is linear in R. Okay, this is the analog of 1 over R to the d minus 3 that we had in higher dimension. Okay, so it's linear in R. And so from this we see that this mode now dominates. So the charge mode is dominant, so it has to be kept fixed. This mode we let fluctuate. Yeah, so you sum over all chemical potential, but this means in terms of the ensemble that is sum over states with fixed charges. And then you can do a similar analysis for the metric, and one can show that we sum over states with fixed energy and angular momentum. Yeah, I'm going to discuss the counter term. Yeah, so we'll see that we don't have to. It's basically coming from a path integral over A, right? So the measure will be fixed just by how you have put the path integral over A, right? And that is normally fixed by gauge invariance, right? You don't really have much choice. In string theory, for example, the measure of integration over the string fields is completely fixed by this BV master equation, right? So you don't really have a choice on the measure.
So Ashok, this black hole is near extremal but sitting inside flat space?
No, it's extremal. It's extremal. Yeah. We are just looking at a strictly extremal black hole.
Should I think of it as sitting inside flat space?
Yeah, you think of it as sitting inside flat space. We're not going to make use of that here.
You're not going.
No.
So suppose I set up the path integral in flats.
Yes.
Then I do something different because then I put boundary conditions there.
Exactly.
How do you go from there to what you're saying here? We break up the path integral into 2 parts, one here, one there. Something
Yeah,
like that.
that's right. Yeah.
Has that been done in detail?
That has not been done in detail. What has been done is to compare the results of these 2 cases, right? Which I'll discuss. That we can do these calculations independently, right? Over the full geometry as well as over this truncated geometry, and they give the same result at the end.
The precise nature of boundary conditions doesn't matter because the ADS is
as long throat. Yeah, exactly. The infinite throat basically separates out whatever is happening at infinity from whatever is happening.
What we did there
Exactly. Right. By the time I come down the throat, that information gets lost away. Yeah, in relating this with Chandra ensemble.
Spectrum, say, Laplacian or quadratic fluctuations, showing that the eigenstates, basically can break up in some precise way into nodes in throat and then nodes away.
Yeah, not a detailed analysis. No, I think no. No. Yeah.
That's the path index. Then you
Yeah.
start with the whole path index. Then you break it up into some fictitious boundary condition here.
Yeah.
Then also integrate over that boundary condition.
That is, I agree. Yeah. Yeah. But that is equivalent. I mean, a more refined version of this is what Sandeep is saying. I think that you actually look at the eigenfunctions of the Laplacian, right? And see how those set of eigenfunctions break up into two sets, maybe one from the interior, one for the exterior, right? And then you just do the integrals independently.
But if you did it, I mean, it would be nice to have an in-principle argument that goes beyond one.
I agree. Yeah. Yeah. Yeah.
You can actually
Yeah.
it out.
I agree. Yeah.
It's one thing which is the trivial level of tree-level analysis, because the boundary conditions are different and so on, one can show that you get the right answer.
Yeah. Yeah.
But that, of course, is trivial.
Yeah. At tree level, the point is from the asymptotic observer's viewpoint, the ADS is just a point, right? I mean, you basically close the horizon, right? Okay. And from the ADS viewpoint, the asymptotics you don't even see.
No, I mean, you have the full bulk integral, you have the full action from the asymptotic observer's point of view, going from the horizon to infinity, and you can break it up into two parts. The
throat part and the asymptotic part, yeah.
Right boundary condition of part corresponding to fixed charge.
Okay.
And then show that, the answer you get from the near horizon is the dominant answer.
Okay, yeah,
And
yeah.
the rest doesn't.
I agree, yeah, yeah.
So that's what you can do. But it's, of course, very trivial.
Okay.
And if it was not exactly extreme, it was some little bit near extreme. Would this change a lot?
Well, it will change actually many things. Some things will change, right? Because I mean, many of the zero modes will get lifted and so on, right? So it's.
But the basic point should go. Right?
That yeah.
Still do an ADS
Exactly. Yeah. Right. But this decoupling is not complete, so you want us to do a much more careful analysis there, right? Which I don't think has been done in the full geometry, right? To do a very, very careful analysis and see.
Might even be nicer to do it. Extreme black hole very clear.
That's true, yeah. Yeah, because then you don't have this IR divergence problem in flat space, right? Yeah.
So, sorry, so for example, the log, the P to the 3/2 term, the people have seen, one way they've done it is just in the full analysis with the asymptotic boundary at infinity. And the other is to do some kind of JT story.
Yeah.
And they agree, but there's not a proof.
Yeah, exactly. Yeah. Okay. This full analysis also, I don't think that it has been done really, I mean, very, very carefully, right? Yeah. Yeah. Yeah, I mean, I think that will, I mean, it will be good to have a full analytic analysis for the full geometry. Meaning the fact that the answer is simple, right, means that there may be a simple argument.
Your point is it breaks up into this and that. Path integral already has this and that, and then something in between.
Exactly, yeah.
How if you
Yeah, cut the path integral and somehow, yeah.
Fix you this geometry.
Yes.
Done from half the other ensemble. That boundary condition itself translates into fixing the chemical potential.
Shouldn't, yeah.
Shouldn't fixing of Q at the throat.
Yeah.
Shouldn't that itself translate to fixing the right boundary for flat space rather than doing some sort of using the lower to match that space.
No, I didn't get the
I think
question.
that's
No, I think if I'm right, I think you're saying you take the fixed case.
Yeah.
Which is the right one.
Yeah.
That should automatically give, when you reproduce that analysis of asymptotic infinity, the result, if you take the correct boundary conditions, which is.
Yeah. But that in that process, right, you will also have to get the Legendre transform. Whatever log you will get from the Legendre transform, you have to get. Right?
it's a very natural mechanism, which is that because you're patching onto flat space, you've not gone all the way to infinity.
Yeah.
And therefore, you have to integrate over that Q charge. There will be this thing,
Yeah.
that thing, and an integral over Q. That's this. And that integral will give you the result.
But the point is, okay, that may be one way to think of it, but if you when you actually compare, right, how are you getting this at how are these two ensembles giving the same result, right? There are some zero modes, right, which are different in flat space and in ADS. Right? Maybe those zero modes are the ones which, I mean, those zero modes are the ones which implement this Legendre transform. Right? So maybe those zero modes are part of the, I mean, those are of course part of the path integral, right? But one has to put them in appropriately to see how those zero modes are achieving this. If we start with the whole thing.
Meaning you start with a boundary condition and asymptotic infinity.
Yeah.
Then you just do that path integral, you should get both the fixed charge guy and some local charge. Because
that is true, but you get more integrals which would not be there in the full geometry. Because here, for example, right, you will get the gravitational zero modes, right? This d phase 1 mod SL2R. Yeah, which is not there in the full space time.
The size of the throat.
Not the size of the yeah. Okay, so it's basically deformed. It's pure gauge, right? Except for the boundary terms, right? It changes the boundary.
But once you glue it on, presumably not pure gauge.
No, that is true. But that integral is here, right?
Yeah.
So you have to see then how this change of ensemble gets freezes that integral, right?
How do you think about that?
See those extra zero modes which are here, right? They have to
Once they made it, you're saying fixed charge.
Yeah.
Have to be undone.
Have to be undone. Right. So I think it will require some involved work to see how exactly these two path integrals match.
But could it be that mode is undone by the fact that you have to integrate over Q?
Well, integrate over Q basically means you are integrating more, right? Not less.
Legendre transform, going back. If you do Legendre transform and go back, come back to the origin.
Okay. Originally is a microcanonical or grand canonical? Grand canonical. Okay. Okay.
That's like the UV.
Yeah. Okay.
Okay.
Yeah.
Now I have fixed Q.
Yeah.
Now if you integrate it over Q, you go back to fixing.
You should, but it's not completely obvious how it happens in this geometry, right? That's what I'm saying. Yeah. I mean, eventually it has to work that way, right? But the details are not clear.
I was thinking it's a separate event. I'm saying Ashoke is setting up a problem that Q is fixed. But in the full problem, Q will not be fixed.
Yeah.
Because you think of it as path integral here, path integral here, and then path integral of that cut.
Yeah.
That's the Q.
Geometric quantity meaning. Well, it's not quite geometric, meaning if you think of the gauge field is coming from some Kaluza-Klein modes, right? Then in the higher, once you include the compact space, it becomes geometric. Right? Otherwise, you just think of this as a gauge field. Right? You can think of it as geometric by thinking of it as Kaluza-Klein mode, but I'm not sure that will really help that much. Right? Because you are just bringing in some additional space time in this picture. For mass, it will be geometric, yeah. That's why I have not discussed the mass and angular momentum, but there are similar arguments, right? Which basically says that in ADS2, you really cannot throw in any charge or mass or anything. It will just change the asymptotic boundary condition. So we really have to fix the mass, charge, angular momentum, everything, and carry out the path integral. And that's the natural boundary condition on ADS2. Okay. So just to simplify notation, we'll just treat J as a component of charge only, because we can just regard K as a compact space, and in which case angular momentum just can be thought of as a charge. Okay, we'll just think it from the point of view of ADS2. Q is a charge, gauge charges. K is a compact space, the S2 or S2, S3, whatever, right? So you just think of the compact space, and then the J just becomes, by Kaluza-Klein reduction, right? You can think of it as a charge as far as the ADS2 is concerned. K is a compact space. Okay. Regarding K as some internal compact space, right? The way you do Kaluza-Klein theory, right? Yeah, reducing over it. Yeah, exactly, right? See, normally K is big, right? In ADS2 terms S2, so you don't think of this as a compactified space-time, right? But we are just thinking, I mean, as far as this analysis is concerned, we can just think of this as a compactified. Yeah. Come down to 2D. Yeah, you can do the analysis in 2D. Okay, so here is the. You are dimensionally reducing, right? Because you are only interested in the low lying modes. Yeah. Well, not dimensionally reducing, not necessarily. You are also including the Kaluza-Klein modes. Think of all of those. Yeah, exactly. So those modes you are not throwing away. But those are also low lying, right? 1 over A square is low lying from our viewpoint. Suppose A is the size of ADS, right? That is also size of S2. So 1 over that size is to be thought of as a low lying. Yeah, because it's the same size as ADS2. Right? But for fixing boundary condition, etc., we can just think of this. All modes are low lying. You have to integrate over all those modes. Okay, so here is a boundary term, right? That in order to account for the changed boundary condition, right? Normally we keep the chemical potential fixed. Now we are keeping the charge fixed. Okay? And then one can show that in order to have a well-defined path integral, we have to add a boundary term like this to the action. Okay, to the minus IQ dot integral d tau a tau. And here this a tau will include the usual gauge fields as well as the components of the metric that come from, that represent the angular momentum, that couples to the angular momentum. Right? That's all I meant by saying that we regard K as a compact space. Okay, so this a tau will include also the g tau phi, for example.
You might have expected as but also a cutoff.
Yeah, there is also a cutoff dependent term, because it's a tau, if you see from here, there is this term, right? So there is a cutoff dependent term, but that will not bother us eventually, right? Because eventually you look for the part of the partition function that is independent of that cutoff. Okay, so then by following the same rule, we see that, so on the gravitational side, we have exponential minus action times f. This is the weight factor. So the corresponding partition function will be given by this. And now this beta mu dot q basically gets cancelled. And you are left with e to the minus beta h plus 2 pi q square r naught. Now this beta is also proportional to r naught, right? Because beta is the period of the Euclidean time circle at r naught. Okay, so you can see the metric, the d tau square coefficient is a square times r square minus 1. So the period at r equal to r naught, okay, is basically integral 2 pi times a times r naught, right? That's the period. So beta is proportional to r naught. So Z then becomes the exponential entropy, right? Entropy is a degeneracy of the ground state. So this trace is taken over all states. So it becomes exponential of the entropy, and then these terms that are linear in R naught. Okay. So from this formula, we see that the information on the entropy basically comes from the R naught independent part in log Z. So you calculate Z using gravitational path integral, okay, on ADS2 times S2, take the log of that, and then the entropy comes from the R naught independent part of that. R naught is a cutoff. We just put some arbitrary cutoff on the on ADS.
What was
Yeah, is the mass or the energy. Yeah.
Remove those terms with an additional counter term.
You can. But the point is, it is, once you compute log z, right, from the gravitational path integral, you can see that there is a clear separation between a terms linear in R naught, right, whose coefficients are not universal, but there is a constant piece which has completely universal coefficient and which can be unambiguously determined from log z. And that's what you identify as the entropy. Well, you can, but you don't want to. R not equal to 0 is somewhat unphysical, right? You can say, you can, you can say it that way, or you subtract of R naught times dd R naught of log z, right? And that is just linear, remove the linear term in R naught. Exactly, yeah. Because you can always add terms which are proportional to the boundary length. And the important point is when you ADS2, when you calculate the volume of ADS2, right? The volume has a piece that is proportional to the boundary length, and then there is a piece which is constant, and the constant part is universal, right? It doesn't matter how you regulate the boundary. You can take any shaped boundary, right? And the volume is always that boundary length plus a constant which is completely universal, right? Doesn't matter what shape of the boundary you take. That is the entropy.
So the counter term will just be cosmological constant in the bottom.
Yeah, that's right.
Fixed
Yeah.
coefficient.
Yeah, with a fixed coefficient times energy. Exactly. Okay. So the important point here is that you don't get any logarithmic term from the change of ensemble. Okay, this gives you the entropy right on the dot, right? So purely gravitational path integral determines the entropy.
The ensemble is about it.
Yeah, because ensemble is already microcanonical, right? You don't change any ensemble in this case. Okay, then we have something in between. Okay, and that's a third example. Okay. This is while computing supersymmetric index. So the supersymmetric index is defined in this way. So we pick some J0 is some particular Cartan subalgebra of SOD minus 1. This is the rotation group. K is the momentum as usual. J prime will represent Cartan generators other than J0. So we define I, which is a function of the charges, and J prime, okay, which means this set, excluding J0. We carry out the trace at fixed Q, fixed J prime, and at fixed momentum, which is set equal to 0, of e to the minus beta h, e to the 2 pi I J0. This plays the role of minus 1 to the f. And then there is a factor of 2 J0 to the n for some integer n. The important property that this trace satisfies is that it gets contribution from only supersymmetric states which break 2n or less J prime invariant supersymmetries. Okay, so you classify all the we look at the set of all the supersymmetries in the theory. Okay. Then you focus on that subset, okay, which commute with J prime. Okay, this Cartan subalgebra that you have fixed. Okay. And then we ask, okay, that which are the states that break 2n or less of those supersymmetries. Okay. And this trace gets contribution only from those states. Okay, so states which preserve some amount of supersymmetry.
Just to understand. So if I turned on a chemical potential, so this is like working at a specific value of chemical potential for J0.
Yes.
Namely 2 pi I.
Hmm.
So if I just made that 2 pi I new for a moment, and then I would have seen that states with 2n supersymmetries would have a factor of mu minus 2 pi I to the power 2n.
Exactly. Yeah.
Because of the number.
Yeah.
And then you differentiate 2n.
You differentiate 2n times, so to bring down this 2J0 to the n. Right.
Then suppose we work with an arbitrary. Now, at mu equals 2 pi I, you would have a factor, if you preserve n supersymmetry, you would have a factor of mu minus 2 pi I to the power. Because each supersymmetry would give you an extra 0.
Which you have to saturate by bringing down parts of that J0, right?
So now you differentiate 2n times to get rid of that. So you get something non-zero, but that's equivalent to bringing down 2n.
Yeah, exactly.
Okay.
Okay. So the special case of this is n equal to 0, right? That's the Witten index. So Witten index basically will count states that break 0 supersymmetries, right? 0 J prime invariant supersymmetries, but in general, BPS states will break some amount of supersymmetry. So if you are going to count BPS states, then you don't set n equal to 0, you set some appropriate value of n, right? So that those BPS states contribute to that trace, but at the same time, n shouldn't be too big, because otherwise every state will contribute, right? Then the index is not very useful. Okay, so you have to choose n to be big enough, but not arbitrarily big, so that supersymmetric states do contribute to the trace, but generic states don't contribute. Okay, so this is what then we want to compute. This is supposed to be beta independent. Yeah, at the end, well, it's not quite beta independent, but beta dependence is trivial because it will be e to the minus beta times the BPS mass, right? Beta times MBPS. So beta dependence is fixed, and it gets contribution only from the a fixed energy state, right, which is the MBPS. Yeah, so this is what I have written here. So this index then will be given by this feature that it gets contribution only from the supersymmetric states which have a fixed mass. So e to the minus beta h becomes e to the minus beta times MBPS. This 2J0 to the n goes away in saturating various fermion zero modes in this trace. And then the degeneracy is what I'm calling e to the SBPS as a function of Q and J prime. Because the trace will fix the mass. When you take the trace is getting contribution only from the BPS states, right? So, and we are fixing K equal to 0. So the energy gets fixed to MBPS. So this is not something that you do by hand, but once it's guaranteed by that, the index will automatically pick up contribution only from these states. Okay, so just to give some example, that in D equal to 4, the rotation group is SU2. So J prime is trivial, right? J0 you can take to be the third generator of the rotation group. So in this case, there is no J prime. Okay, it's a function of the charges only. In 5 dimension, the rotation group is SU2L times SU2R. So you can take J0 to be part of one of the Cartan subgroup, okay, and J prime as a part of the other Cartan subgroup. And in this case, SBPS will be a function of J3L, because that's J prime, and the other charges. So now we look at the left hand side, which is the how to calculate this index gravitational from the gravitational perspective. And that is not hard because it's the same kind of trace that we had, right? This is a special case of the same kind of trace that we had. So gravitational prescription for this is clear. We first of all set beta omega 0 equal to minus 2 pi I. Omega 0 is the chemical potential dual to J0. Okay. So we set beta omega 0 equal to minus 2 pi I, so that you produce this to the 2 pi I J0 factor. Okay. And then we have to insert this 2J0 to the n factor in the path integral. Okay. So this is what we do on the gravitational side. Okay. And this calculation is again done in flat space time. Okay. So we integrate over all the charges, right? We don't in the when you do the gravitational path integral, you are integrating over everything, right? Fixing the boundary condition as a chemical potential is being fixed at infinity, which will be a function of Q and J, right? But as far as the gravitational path integral is concerned, right, we fix the chemical potentials and we have to integrate, right? Because you don't know how, from the gravitational path integral viewpoint, you don't know how to fix Q and J, right? So that you have to relate to the index now.
There is this EDS2 way that you first talked about, then you could just directly.
Yeah, then you could directly get it.
And there would be no problem in it.
Yeah, yeah. Well, there will be some problem in doing that because this demands that we fix the chemical potential, right? In ADS2, you cannot fix chemical potential.
So you cannot.
So you cannot compute it directly in ADS2. You have to go to flat space time.
All you want.
Yeah, you have to fix the chemical. You are fixing chemical potential, right? In ADS2, you don't know how to fix chemical potential. These calculations you have to do in flat space time. Yeah. There are indirect arguments that in ADS2 the degeneracy is the index, right? So from that you say that, okay, what you have calculated is the index, but if you want to calculate this object, right, you have to do it in flat space time.
But in some sense, can't be better than ADS because you can then here you're not computing things as a function of all charges. Because one of the charges, one chemical potential is fixed.
Yes.
Now in your ADS, you could compute things as a function of all charges.
Yes.
So isn't that more information?
Well, it's eventually it's not really more information because you are counting. Ultimately, you get the microcanonical result, right? In ADS2, from here also you are going to extract the microcanonical result.
No, sorry. What I was saying is that you're extracting microcanonical with respect to the charges that you can make.
Yes.
But there's one charge that you cannot, namely this J.
Yes. In ADS2. Well, meaning, yeah, this charge in this case, you have to vary J0. We fix omega.
What I'm saying is that you will not be able to get information on number of supersymmetric states as a function of this.
Yes, that's true.
Okay. Whereas if you just did the calculation in ADS2, not trying to compute the index, just computed the number of states as a function of charges, you will also get the answer.
I agree. Yeah, I agree. Yeah.
So in some sense, that's a better calculation.
That is true. Yeah, that's a better calculation, but yeah, I agree, right? Because of the conclusion that you get from ADS2 is that all states have J0 equal to 0, right? Based on this, the rotational invariance argument. Yeah. So at the end, you get the same information. Okay, you get a little more that all the index is coming only from the J0 equal to 0 states, right? Whereas here,
you wouldn't have known that.
You wouldn't have known. Yeah, here you wouldn't know that all states are J0 equal to 0. Yeah, I agree. Yeah. Yeah, it fixes SU2 invariance. Yeah. Here? Yeah. So this is the gravitational path integral, right? So let's look at, so gravitational path integral, what we are saying here is that we want to, so gravitational path integral is in the grand canonical ensemble, right? You have trace over everything. Okay. Now here you see in the definition of I, you have already traced over J0. That's gone into the definition of I, right? So when you want to relate Z to I, you only have to integrate over Q and J prime, right? And K, right? J0 is already traced. In the definition of the index, J0 trace has already gone in. It requires 8 total unbroken supersymmetries. That of which 4 are the superconformal ones and the 4 are usual supersymmetries.
That was 4 dimensions.
That argument, I think, if you have 8 unbroken supersymmetries, that is good enough because you have SU112. Okay, it was given to strictly in 4 dimensions because otherwise the group structure itself will change. Yeah, that is true.
So I was wondering, in 4 dimensions, just say J0 and 0. There's no term.
Yeah.
But in higher dimension, are you going to get that all angular momenta? Right?
I think in higher dimension, we will probably find this J3R equal to 0.
All J.
J3R.
J3R.
J3L, you can, because it becomes SU2L times SU2R, right?
Yes. So basically, one rank lower.
Exactly. Yeah.
Than the post J.
Exactly. Yeah.
That's
So you fix one of the angular momentum to 0. Exactly. Yeah.
So in general, in higher dimensions, the angular.
Well, above this, there is nothing, right? You don't get you don't have a black hole with regular horizon. So 4 and 5 are the only 2 playing fields. 5, the algebra is, so there is SU2L times SU2R, right? The rotation group is SU2L times SU2R. And I think what you can, based on this symmetry argument, you can say that the J3L, the SU2, it should be SU2L singlet, right? SU3R can be anything, or vice versa. So one of the angular momentum you fix to 0.
And that uses the special decoupling of SO4 into two groups.
Exactly.
It's consistent for
Yeah.
to be 0 and
Yeah.
no constraint.
Exactly.
That doesn't mean some particular index equal to, right? Because you could have fermions both being.
Yeah. If you define the index as being weighted by e to the 2 pi I J3L, and then J3L is equal to 0, right? Then index will be equal to degeneracy. So don't use -1 to the f in the index, but e to the 2 pi I J3L, right? You can define index that way.
LR symmetry is broken because you choose one non-zero chemical potential in one.
That's right. Yeah.
So
Yeah.
it doesn't matter which one.
Exactly. Yeah. Yeah. And above 5, we don't have any black hole with non-singular horizon. Extremal, the BPS black hole is non-singular horizon. Yeah. You have the small black holes, but no regular black holes. Pardon?
Yes.
ADS you have, yeah, in flat space. It is in flat space, yeah. Okay, so Z is then related to the index in this way, right? So this is similar to what we had earlier, right, in the example 1. Okay. And these integrals will produce additional log lambda factors, but there is slight difference because these integrals, the sum of the integrals are removed, right? There is no J0 integral here. Well, two less, because M integral is also gone. M, right? M gets fixed to M BPS, right, by the BPS condition. So M integral is gone and the J0 integral is also gone. Yeah, so there are logs, but there are different kinds of logs that you get. Here, but the analysis is similar. Okay, so now I go to the other side, how to evaluate Z.
Right. Suppose you had not been clever enough to realize that N was fixed once you fixed all other charges.
Yeah.
And you just tried to do the integral. That integral should have localized that to a delta function automatically.
Yeah, yeah. The saddle point fixes M, right? Because you look for symmetric saddle points, right? And you find that fixes M automatically.
But I think measure factor also should automatically have gone.
Thickness factor, okay. I think the point is if supersymmetry fixes M, right, then you don't integrate over M anymore, right? Because then you lose the you have to integrate over the supersymmetric subspace. If you try to go outside a level, you will get too many zero modes, right? And those zero mode integrals will kill you.
But suppose you hadn't realized all. It doesn't sound wrong to integrate over M. The calculation should have told you get only a delta function contribution.
Yeah, that is by the fermion zero mode integral.
Yeah.
Right? Well, yeah, because once you go beyond this subspace, there are more fermion zero modes, right? And they will just give you 0.
So you get 0 things.
Exactly. Because this 2 J0 to the N is the one which saves you from the fermion zero modes, right? And if you have more fermion zero modes, then you will get 0.
SBPS was the thing from the index.
Yes, exactly. SBPS is basically the exponential of the supersymmetric ground state degeneracy, right? But microcanonical. Yeah. So basically, I defined SBPS by this, right? But this is really counting the total number of BPS states with these quantum numbers, Q and J prime.
And so in this part, how do you insert the two J0s, the two J0 in the flat space calculation? How do you put the two J0 to the pi?
Yeah, so it's there. Oh, I forgot to write it. There should be 2 J0 to the N here. Right?
But is that done by putting derivatives on the chemical potential?
2 J0 to the N? No, you just put 2 J0 to the N. Right?
I thought you were fixing chemical potential.
No other current. Okay.
Sorry,
No. There is no J0 here, but there is an author current, right? The J0 for in the flat space, you can construct J0 as the author current. No, inside the path integral.
But measure that integral.
No, in the bulk. Doesn't matter. It's anywhere, right? On a special slice. Okay. The point is that that's somewhat trivial because this path integral has some fermion zero modes. Right? So you have to get rid of those fermion zero modes. Right? And the only place which can get rid of fermion zero modes is from inside J0. Right? So J0, of course, gets contribution from zero modes, non-zero modes, everything. Right? But you have to just pick up the zero mode part. Right? Because otherwise the fermion zero modes will not be saturated. Right? And you have exactly the only way to saturate the fermion zero modes is that you have to pick up the fermion zero mode contribution to the J0. Right? From each of these. Yeah. Yes.
That has integral over fields and that has fermion.
Exactly.
On the right side, you seem to be saying you're going to put J0.
No, sorry, not right side, sorry, left side. Yeah. On the left side, in exactly. Yeah. So Z is the Z which, because here the J0 insertions are already there in the definition, right? Yeah, exactly. Because here in the definition of this itself, there is a J0 insertion. So Z evaluation will have to have the J0 insertions, right? And those J0 insertions basically will supply the fermion zero modes and then won't do anything.
But J0 is just defined as classical vector charge.
Exactly, classical vector charge. True. No, but you are only interested in lambda dependence, right? It doesn't matter the details of the wave function, right? Those are the lambda scaling is what you are after, right? So for that you don't have to worry about constructing details of the wave function. Exactly, that's right. Yeah, that's good enough. Okay, so now the evaluation of Z, in fact, this should be easier because this is more or less standard. So if Kb is the kinetic operator for the massless bosons and Kf is the kinetic operator for the massless fermions, then the one loop contribution to Z from massless fields, right? This is where the log lambda comes from. So I'm going to focus on this. Is the determinant Kb to the minus half times determinant Kf to the half. Right? It's actually the Faffian of Kf, but as far as lambda counting is concerned, it doesn't matter. We can just think of it this way. So this gives you a correction to log Z, right, which is just log of this. So minus half log determinant Kb plus half log determinant Kf, okay, which you can also write it this way. And now the lambda dependence in these come because the Kb, this is the Laplacian operator, this is the kinetic operator for massless bosons, right? This has two derivatives contracted with G upper mu, right? So that goes as lambda to the minus 2. And similarly, Kf goes as lambda to the minus 1, right? Because it has only one derivative. So we get some lambda dependent contribution here, lambda dependent contribution here. And there is a standard method, the heat kernel expansion, that lets you compute what this contribution is.
So naively is lambda to the power infinity.
Yeah,
There's a subtraction.
exactly. There's subtraction, but that heat kernel automatically takes care of that.
Lambda, now thinking of it just like size of that.
Yeah, is the total number of eigenvalues, right? What you're counting, this, see, each eigenvalue gets lambda to the minus 2, right? So you are trying to count the total number of eigenstates of the bosonic operator and total number of eigenstates of the fermionic operator, right? Those, as you said, are divergent. They're both infinity, right? But the heat kernel gives you a regulated version of that. And that's what you are counting.
I was trying to understand that physically. These modes are outside the black hole. Now, as black hole becomes bigger and bigger,
Yes.
it's like you have fewer and fewer modes. Is that right? Because the space outside is becoming smaller.
That is if you fix the size of the box, size of the.
You're fixing something infinite.
Yeah, you can think of it that way, but the heat kernel, if you work in the full space time, right, then the heat kernel actually is gives a finite result. Okay, there is cancellation between bosons and fermions.
Oh, it's finite.
Yeah, because you basically get something in integral of Riemann square or Riemann times f times f. So these are normalizable integrals, right? You don't really have to do much.
So you're saying though there's an infinity, most of it cancels.
Exactly.
So it's not like you have to regulate.
Yeah, you get a finite result. In ADS, you have to regulate. In ADS, you get a volume integral, right? And then again, that volume integral, you have to write it as a surface integral plus a finite constant, right? That decomposition is completely unique, right? And in that way, you can get a extract an unambiguous result from there. But in flat space, right? It's really a finite integral. Yeah.
You introduce this finger, whatever, proper time cutoff, you get a series.
Yeah.
Is it the log epsilon term that is corresponding to the log lambda?
Yeah. Log lambda term is basically integral from epsilon, the cutoff. If the UV cutoff is epsilon, right? We are taking that to be of order 1. It goes from there to lambda. Right? So it's basically that you have a lot of eigenvalues, right? Eigenvalues are all of order 1 over lambda square. Okay? And it's the upper cutoff, right, is of order 1. That is the UV cutoff. Okay? And that the log comes because it's the ratio of the UV to IR. Right? IR is of order lambda square and the UV is of order 1.
And ADX, you don't have this cancellation because you're not computing anything. Because you're not doing the -1 to the ADX.
No, here actually you don't really need -1 to the F. See, there are divergences in the heat kernel. What happens is that there are divergences which come from, okay, let me put it this way, that it's not that it's finite. Okay, what is finite is the coefficient of the log lambda term. Okay? Because it's log lambda over epsilon. Right? Epsilon is the UV cutoff. So if you really take the UV cutoff to infinity, then it will be infinite. Okay? The reason that you are getting a finite result is because we are taking the UV cutoff to be of order 1. You assume that you are working in string theory or whatever, right, which has a natural UV cutoff, and you are writing everything in terms of the UV cutoff. Okay? So this lambda, for example, is the area measured in the units of the UV cutoff.
So if I just did an effective field theory calculation, I would get some infinity.
Yes.
But that infinity would have different lambda dependence than log lambda.
No, that infinity probably will come from as log lambda over epsilon.
Okay.
Right?
So
Epsilon goes to 0 limit is infinite.
fine. But you can isolate out the part that is log lambda.
Exactly.
You write that as log lambda minus log.
Exactly. That's right.
I see.
Right? So log lambda dependent part is not divergent. That's the point. It's not all divergences go away.
And yeah, that is log lambda. You say it comes from the scale. Sorry, let me ask whatever. If I have a box and I have many modes in the box,
Yes.
The entropy often scales like volume, not like log of volume.
Okay.
I was thinking of this lambda as being some measure of what part of the space-time you've eaten out by the black hole. And I'm trying to understand why that your dependence is only log lambda. Maybe there's a volume term which you're throwing away.
No, there are 1 over lambda terms also. Yeah. So there's a whole series.
Okay.
Right? So of that, we are just focusing on log lambda term. Exactly. You are only interested in log lambda term.
Higher power of 1 over epsilon to some power. Right?
Yeah, exactly. So the G Newton, the non-extremal of G Newton, right? That is of course always there. Right? But you are assuming that you are already working with extremal as G Newton. Right?
And if I was just doing free calculation in a box, and I computed the partition function, just free scalar field theory in a box of cycling.
Yeah.
And I computed, if I then Taylor expanded in 1 over V, would I find the log V? Is it?
Yeah, you will probably find the log V, but I'm not sure that log V is the same as this one, because maybe you will find, right? Because you are saying there is 1 over L square. Things are given in terms of 1 over L square, right? But I'm not sure, because there what will happen is that, see here the integral over that box is just the integral over d4x, right? The integrand which multiplies log lambda is a convergent integral because it's Riemann square, for example, right? If you integrate Riemann square in a flat space time in the black hole background, you get a finite answer.
So it's not coming from a fluctuation, it's just coming from evaluating a particular term in the action.
Particular term in. No, you cannot do. See that the point is you cannot first define the effective action and then do the integral, right? That's why you need the lambda, right? Once you have gotten the lambda, right, then you get a term proportional to log lambda, and then you have an integral. So that one shouldn't think of this as an effective action evaluated independently of the black hole background, right?
Because quantum.
Yeah, because it's quantum and it, I mean, even if it's quantum, you can sometimes construct a local effective action, but this is not local. This is because there is infrared. So lambda appears in the infrared cutoff, right? So it's not that it's the size of the box which is controlling it. Right? Because the eigenvalues themselves are somehow controlled by lambda.
But that's because the size of the box is large.
I think it's more, it's that the curvature and everything scales as lambda, right? It's fixed by lambda.
So
Right?
the spherical box, if we were on a sphere of size 1 over r, then we will get one log r.
If you do this calculation, you will not, because r Riemann square is 0 inside, right? At least this way of doing the calculation will not generate that. Maybe there is some other way to do this. Yeah. Meaning because this is a bulk integral, right? The way it appears at the end, right, is a bulk integral, right? This is in fact, I can show the form, right? So the final integral, final expression using the heat kernel has an integral of this form, right? Where k of x is something that you can calculate once and for all for a given theory, right? Once you have the massless spectrum and their interactions, you can calculate this heat kernel k of x, okay? And then the log lambda dependence is just this integral.
Sorry to be disruptive, but why is it so simple? As you said, it was coming from some IR divergence. Why is it so simple?
Well, it basically comes because you have this in sum. You are trying to count the sum over n 1, right? Okay. So the way you do it is you write it as integral d4x or ddx sum over x, sum over n, psi n star psi n, where these are the wave functions, normalizable wave functions, okay? Because integral d4 ddx psi n star psi n is just 1. Okay? Then you write this as integral ddx kxx, okay, where kxx is given by this sum. Okay, so this is what you calculate using heat kernel. Okay. This kxx has the lambda dependence because psi n's depend on lambda. Okay, and then you make an expansion of this. So this kxx is given in terms of heat kernel, but then it has an expansion like integral ds times 1 over s to some power, then 1 over s to another power, and then finally you look at the 1 over s coefficient. Right? This is what gives the log lambda term. Right? So all of these are divergent. Right? But these divergences you reinterpret as either renormalizing the cosmological constant or renormalizing the Newton's constant. Right? And then so it's not that these are free from divergences. The infinite number of modes, of course, will cause divergences, but those are like divergences that renormalize the various local terms. Right? And the non-local terms is basically logarithmically divergent term. Okay, that's what gives the log lambda. And this integral, right? So there you see 1 over s coefficient will also have some particular function here. That's what I'm calling kx.
Since it's so simple, because the divergent terms correspond to local counter terms, and the log is not local, but it's log of epsilon over lambda.
Exactly.
And that epsilon is still the log, it's a unitary. So
exactly. Yeah. 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 Though for log lambda, those are not important. Yeah.
Yes.
This is just some auxiliary variable that you integrate. This is proper time, right? To the minus m square s integral this. That's yeah. Then you may get some. If there is a local variation, say unless you have a local variation in geometry, right? At least this heat kernel method doesn't seem to be giving anything interesting, right? Because it really comes from here. And as I said, I mean, here, if you have supergravity with n larger than or equal to 2 supersymmetry, then one can show that this is actually proportional to Gauss-Bonnet term. So the integral becomes very simple to do. right? Otherwise, it's a big headache to do this integral because it will have, say, in integral Riemann square in a in some background, right? Or Riemann times f times f. So those integrals you have to do, but for n equal to 2 and higher supersymmetry, you just get Gauss-Bonnet. So it's just a Euler number of the black hole space-time.
All you are doing is counting number of.
Exactly.
All you're
Yeah. All you are doing is counting number of modes, right? But there is a regulated version of that, right? Because as I said, there are divergences, and the regulated version, the part that you are interested in, right, that has a simple structure.
So this in principle doesn't need gravity or anything. It could be just field theory in this background space.
Yeah, exactly. But I mean, key of x, of course, does depend on the gravitational background.
Yes. But
Yeah.
it could be just field theory in.
Exactly. Yeah. This is field theory in Chord space, right? Even the metric fluctuation, you just think of this as fluctuation in the Chord space. Exactly. Because it's a one loop determinant, right? I mean, we don't expect that you don't need more, very much more than that. Exactly. That's right. Right? And it's a regulated number of modes because
Because it's a volume.
Yeah, exactly. Yeah. Okay. So the point is, this is the non-zero mode contribution. Okay, this is actually not the non-zero mode contribution. This is the point. Let me explain this. Okay. So the point is that KB and KF may also have zero eigenvalues, right? Which arise from broken symmetries like translation, rotation, supersymmetry, etc. And these cannot be treated as part of the determinant, because clearly the zero eigenvalues are not to be treated as part of the determinant. So the idea is that you have to first remove their contribution from delta log z. Okay. So for example, the bosonic mode gives a contribution of 1 over lambda squared to the minus half, right? As we saw here, because each KB goes as lambda to the minus 2, right? So each bosonic mode gives you lambda to the minus 2 to the minus half. Okay. So it gives a contribution of log lambda to log z. You have to first subtract log lambda from log z for each bosonic zero mode. And similarly, we add half log lambda to log z for each fermionic zero mode, because fermionic zero mode gives log lambda to the minus half. Okay. So this is the first step, that heat kernel somehow includes the zero modes as if they are non-zero modes. We have to rectify it by subtracting that contribution. And then we have to find the actual lambda dependent contribution to z from the zero mode integrals. And this is somewhat involved, because the way one does the zero mode integral is that typically the zero modes arise from some broken supersymmetry. For example, the translation mode, right? The translation symmetry is broken by the black hole, so that gives a translation zero mode, right? If it's a rotating black hole, it breaks some rotational symmetry, so it will give some rotational zero modes. So it arises from broken symmetry. So the first step is to express the integral over the zero modes as integral over the broken symmetry parameters, and then we carry out the integral. And the same thing we do for the fermionic zero modes, right? Fermionic zero modes are typically associated with broken supersymmetry, and these eventually will be saturated by the zero modes coming from this 2J0 to the n. So the point is that in this integral, the original integration method can have some lambda dependence. The Jacobian for the change of variables can have lambda dependence. And the integral over the symmetry transformation parameter can also give powers of lambda. And all of these will eventually translate to log lambda in log z. Okay, then you have to take into account all of these steps.
Like some integral over some resulting group manifold of the symmetry and so on. So starting from, say, the usual ultra local measure in the gravitational part of the you change over it.
Exactly. So I have given an example, right? So let's try to go through the example. I think I have maybe in 8 minutes I can try to finish, right? Because at 4 o'clock the next thing starts.
The famous confound factor.
Oh, that, as I said, we just rotated determinant. Non-zero mode integral, non-zero mode determinant, right? In this heat kernel, it's automatically assumed that you have done all this Euclidean rotation.
Sorry, later, and your answer will depend on that.
No, you get a factor of I from the rotation, but that doesn't affect the log term, right? Yeah, we are not testing that. Yeah. I mean, we are testing that it is somewhat sensible to do that, right? Because we are getting the final correct answer. Okay, so here is just an example, right? In asymptotically flat geometry, there are translation and rotation modes come from broken bosonic zero modes, broken supersymmetric is fermionic zero modes. And in near horizon ADS 2-term K geometry, the diffeomorphisms that do not vanish at the boundary but generate normalizable deformations of the metric, these actually give a lot of zero modes, right? They are in D phase 1 mod SL2R. And the superproducts of these will give you fermionic zero modes, which basically reduce to superpara zero. Yeah, this is for the ADS 2 times K, exactly. So for this, the zero, so the main thing I'm trying to emphasize is that zero mode structure is different depending on whether to do the ADS calculation or the flat space calculation. Okay. Nevertheless, at the end, if you calculate the same thing from the two different viewpoints, the answer should agree.
It depends on the
Measure depends on the which modulus? Yeah, it could, yeah. But we are only interested in extracting lambda dependence. Yeah, that doesn't, you can separate out the lambda dependence, right? So I think if this example, this may become, make it clear, right? So let's look at just the translation zero modes in flat space, right? How do you do this calculation, right? Do you do it from beginning to the end? Translation zero modes in flat space. Okay. So translation zero mode will basically come through H mu nu, okay, a deformation of the metric. Okay. So first, let's fix the integration measure over H mu. Okay. So let's suppose that it's d of lambda to the alpha H mu nu for some arbitrary, some unknown constant lambda. Okay. And then the demand that we make on this integration measure, this is the ultra local measure that Sandeep was just referring, is that whatever this alpha is, right, this integration measure, and this exponential factor should give you 1. Okay, that's where you know lambda dependent contribution from this integral. Okay, that's how we're going to fix alpha. Okay. This is the ultra local measure that one uses for a path integral over all fields in the theory. Now, in d dimension, this scales as lambda to the d minus 4. So you see that this exponent will have a lambda to the d minus 4 times h mu nu h rho sigma. So here, if you choose alpha to be d minus 4 by 2, right, then this integral will have no lambda dependence. Right? So that's how we fix alpha. That we choose alpha to be d minus 4 by 2 so that this integral gives you order 1 without any lambda dependence. Next, we change variables. Right? We change variables by identifying the zero modes as translation by some vector sigma. So the actual zero mode deformation is generated by these diffeomorphisms, where you take the diffeomorphism parameter to be c mu times the function of x, where f of x approaches 1 at infinity and 0 at the horizon, right? Because you don't want to move the horizon, right? We keep the horizon fixed and we move the asymptotics by a constant that basically translates the black hole in space-time. So then we change variable from h mu nu to c mu, okay, which is given here. Okay. And the main point to note here is that we have to lower c, right? Because the natural translation parameter is c with upper index. Okay, we have to lower the index of c, and this will give a factor of lambda square because g mu nu is scales as lambda square. Okay. So then that Jacobian from change of variable from h mu nu to c will give you lambda square. And final step is to find the range of C. So to do that, we put the black hole in a system of a box of physical size L. Right? L we take to be much larger than the typical size of the black hole horizon. Then the range of the coordinates is of order L over lambda, right? Because g mu nu is lambda square, right? So if you want the physical size L to be fixed, right, then the coordinate range should be L over lambda. Right, because you have to multiply by the square root of g, square root of g xx or whatever, right?
So you're using the same box independent.
Yeah, we are using the same box independent of lambda. Okay. So the range of c mu is of order L over lambda. So then the zero mode integration, the net factor that you get is lambda to the alpha right? Because that was involved in the H itself, right? Then lambda squared, which came from the Jacobian, and lambda inverse, which is the range. Right? So this is the net contribution from the zero mode integral. Okay, where alpha being d minus 2, 4 by 2. And the same analysis, similar analysis can be done for the other zero modes. So at the end, the consistency check is that the index or degeneracy of supersymmetric black holes, we can compute in two ways. We can either work in a near horizon geometry, where the path integral directly gives the result in the microcanonical ensemble, and the logarithmic corrections come solely from the path integral, right? No change of ensemble or anything. Or you can work in the full geometry and compute the index, in which case we have to take into account the logarithmic terms that come from the change of ensemble. But at the end, we get exactly the same final result, right? In all the theories that one can study, this is the case. No, this has been done all in the asymptotically flat spacetime. Right? In asymptotical ADS, the point is that the scaling, right, will also have to scale n. Right? Okay, I think, yeah, we are finishing. Yeah, I think this is the end of the thing. Yeah, so we can just finish.